Yeah, that would be better.
Okay. So we have some issues with the video. I'm still going to start and talk about organizational stuff. Is it working?
Yeah.
Okay, the video's up too. Hi everyone, welcome to the very last regular lecture for visualization. Today we'll be talking about design and evaluation of visualizations. But first we'll do a quick recap of last lecture on storytelling and visualization, and then kind of talk a little bit about the exercise that we did in the last 10 minutes. A couple of organizational things. As you're probably all aware, Saturday midnight is the project deadline. As for the milestone to submit to kind of like conclude your project, please create a release for your repository. Before that time, we will be looking at that release. Also, don't forget to put up your project website. Project website, we recommend that you use GitHub Pages. That's kind of simple to do. You simply have to create a GitHub gh-pages branch for your repository. But also, if you host it, especially if you host it somewhere else, link to your project website from your repository, from the README in your repository. Then you also have to create a screencast. Remember that. The screencast is really important because this is what we will be using essentially to communicate your projects and to judge the best projects. And we will also be showing the screencasts in the lecture on Tuesday. So upload those to YouTube or Vimeo or any other video platform that you like, and link from your README again. Your process book, same thing, link from your README and include it in the repository. So don't forget those things, and those are also like graded in separate rubrics. So you're like, these are kind of like sure points if you do a good job on those, and it's also like a sure loss if you don't do any of those. As I just mentioned, next Tuesday we'll have best project presentations and awards. Remember that we select a handful of projects for like essentially honorable mention. Those are like listed on the website, and we show the videos in the lecture. And then we select one or two or three, depending on how many are outstanding as our best projects of the class. Those get like 20% extra credit, and there will also be physical prizes that we give out. Next Thursday, we have the final exam coming up. The content for the final exam is everything that wasn't covered by the first midterm. So lecture 13 until today, except for the guest lecture, because we don't have slides for the guest lecture, and we also don't have a video recording for the guest lecture. So I think it's unfair for, like, you can't really learn about that. Also remember, there's two papers that all the 6630, the graduate students, have to read. That's the storytelling paper that we talked about last, like on Tuesday, and the nested model paper that we'll be talking about today. Okay, any questions about exam? I, again, unfortunately won't be here, but I have organized somebody to proctor the exam, so it will be similar to last time. Great. Okay. So storytelling. We mentioned that storytelling is an important component for data viz. I also encourage you to really put in the storytelling component into your final projects. And why is storytelling with data and visualization a good thing? Well, it's because you can underscore any arguments that you might make in text or in narration with data and facts. And the easiest way to present data or facts is by simply showing it using visualization. So we can show easily trends, we can show correlations, we can show outliers, and we can convey magnitudes. Let me kill the light here. So like this is a good graphical story, like a static story as it would appear in the newspaper print. Like the characteristics of a good story is that they have a meaningful title, an introduction, something that draws people in, gives them a quick overview, and then a subtitle for a little bit more context. Then what is really important about data stories compared to exploratory visualization tools is things like annotations and like highlights for important observations. So essentially, you don't just show the data, but you tell a story about the data and you emphasize the points that you want to make. As in any visualization, legends are of course very important. Then here we have the main story. In this case, this was this like career progression of various baseball hitters and this one person who is suspected to use steroids, and we see this like increase in his hit performance here in the middle, which is highlighted, which is here the key point that is kind of explicitly called out. The key point of the story is this area here. It's explicitly called out and annotated. And then we have more context, so it's like a deep story. We have some matching on the content. It uses consistent visual encodings here, uses the same types of lines, the same colors for these different peoples, but focuses in on a specific region of interest. And then it gives us more in-depth information with a technique that's called multi-messaging, where we get more information about other players and then different perspectives on the same story. And then we read this paper by Siegel and Hare, where they classified different types of data stories. These were like magazine style, annotated charts, petition posters, flowchart, comic strips, slideshows, film, video, and animation. And one major factor here was the distinction between author or reader-driven stories. Like, what is an example of an author-driven story? Like the most author-driven possible? Could you speak louder?
PowerPoint.
PowerPoint, yes, like what I'm doing here, but I'm also trying to get you engaged. Well, a video, right? Like a data video, as we looked at a couple of times, they are very clearly author-driven because we don't influence the progress of the story. Whereas on the other side of the spectrum, we have readers-driven stories where we don't have any ordering. That doesn't mean that it's not a storytelling visualization, right? We had examples where you can simply find multiple entry points into a story. There's no linear ordering, there's not necessarily messaging, and there's free interactivity. And then these guys also identified these specific types of stories, the martini glass structure, where you start with an author-driven story and then drop people into an open exploration at the end of the main authored story so that you can essentially engage with the data later. Another version is the interactive slideshow, which is essentially like a couple of martini glasses stacked together. You have multiple main storylines, and then you can always branch out. And then the drill down story is where you essentially just provide a lot of different narrated storylines, but you don't necessarily prescribe the order in which to take them. And so then we talked about a couple of strategies for storytelling, to use things like descriptive titles, descriptive subtitles, annotation, and saturation. So here's a comparison between some like very neutral reporting that isn't really storytelling, that's something like you would have in a scientific paper, like ice cream flavor preferences based on 2014 survey of elementary school students. Here we have a little data story. The chocolate was the most popular flavor, and chocolate is highlighted here. Of course, very simple, but it illustrates the principle here. And then we talked about the role of interactivity in data stories. And so we mentioned that we had navigation, things like stappers or scrolling telling, play, forward, rewind, and so on. And then these martini glass structure approaches are very often enriched with details on demand, where I can zoom in onto a particular point of interest. And then the one thing that I really think is a very good approach is ways to make it relevant to the reader. Like, ask people questions that kind of like the story adapts to. What do you think? Who are you? Where do you live? So essentially to make a story relevant to the person that consumes them. And there's really good techniques of doing them. So for example, if you have a data set like we had here in this temperature data set, we could put in our hometown, right, to see how climate change affected our hometown. We don't have to look at just some random city where the publisher of the story lives. And I also highlighted this particular way of essentially asking people for opinions and prior knowledge. So this was an example where you were first asked to draw the relationship between the percentage of children who attend college versus the income percentile of the parents. And this way, essentially, you kind of engage much more with the story, you reflect much more about what is going on, you check your own beliefs, and then they present you with the actual data and also with the beliefs of other people. So these are very engaging ways of getting people to interact with your data stories. And then we ran this exercise where we analyzed these 3 different stories. Where we had this 1.5 million missing black men, the climate change visualization, and then the swing state from the New York Times. Okay, so let's take a look at those. For the missing black men, what's the genre of this story? So I'm going to open it up. So here we have this missing black man story. 1.5 million missing black men. So what's the genre here? We had the options that we had, like essentially we have the visualization for every 100 black women not in jail, there are only 83 black men. This is like for all of the US, and then there's for various cities, for Ferguson, for North Charleston, and then the same gap for whites. And so then we have a lot of text, and then we have again a visualization, where we compare, like in this case, distributions between blacks and whites. And then we have the map of the US, where we see all of these different districts where there is like a strong disparity, and so on. So remember, we had these types of stories, like is it a magazine style, is it an annotated chart, is it a partition poster, flowchart, comic strip, or video? It's magazine style, exactly. So we have a lot of text, which is supported by a couple of pictures, and let's talk about this a little bit later. Is this story author or reader driven?
Reader driven.
Reader driven? What are your choices? Yeah, it's author driven. It's a linear story, right? There's text. You can skip parts. You can also skip parts in a video, but it is basically as author driven as it gets. Is this like a particular structure, like a martini glass or interactive slideshow or drill down story? It's not really, right? It's just like a linear magazine style story. It isn't in any of those classes here. Is it like a good introduction? Is the story like opinionated or neutral? Did you find this was a neutral piece or an opinionated piece? So what would make this opinionated? Like remember the Iraq's death toll visualization that I showed last time, where there was like a very, very strong association with the chart and blood, right? Was there something like this in this particular story? No. So it is not like an apolitical topic, of course, but it is not necessarily presented in a very opinionated way. That would be my judgment here. Well, it does use titles, legends, and highlights well. What about interactivity? Did you interact with this story? So there is no interactivity in this story. And I would say the visualizations are generally quite well designed, right? They use good visual encodings. Yeah?
What medium is used for the introduction?
I just meant like, are there, like, does it properly explain what is going on in the story? And in this case, I would say because there's a lot of text that explains exactly what is going on, I would say it does that. So then we had this story, which is quite different, right? So we had this scrolly telling story about the Earth warming. So we had what is really warming the world. And so here we see first observed temperatures, and then as we scroll, we see different hypotheses, like is it the orbital changes? And we can see that essentially the temperatures fluctuate not because of orbital changes. Then we can see, is it the sun? Is the sun increasing? We can see basically the effect of the sun is really almost negligible. Is it volcanoes? And we see that there is quite some effects of volcanoes, but they're not necessarily making the climate hotter. We can see a combination of all of those things and so on until we find, let's say, things like deforestation or ozone pollution or aerosol pollution or greenhouse gases. And then we see essentially that the greenhouse gases line tracks quite closely with the observed rising temperatures. And so then it essentially drops us into like this, where we can explore this by ourselves. a little bit at least. We can like pick all of these different factors and play with them. Okay, so this is quite a different type of story. What's the genre that we have here? Raise your hands, and then I hear a lot of murmurs, but nobody showing any hands. So what's it? Yeah.
It's a chart.
I would say an annotated chart is usually something static. This paper in 2010, this classification, like they didn't have these scrolly telling interfaces back then, so I would say the closest is a slideshow where we had these stepper interfaces. Is it author or reader driven? Yeah, so it's somewhere in the middle, right? It is a linear story, but we have some control. Does it have a particular structure? Like, is it a martini glass story?
It's interactive slideshow.
It's an interactive slideshow, but at the end it drops you into this like mode where you can actually explore it yourself, right? So this is like a very typical martini glass structure story. And in the interest of time, I'm gonna like skip over the other ones. Other than like anybody, did you like the visualization? Was it well designed? I think the story makes a good point. It also kind of like takes the narration by like exploring all of the different explanations that could be swirling around in your head, and then compares it to the reality. So it is a well-told story, I think. And then we have this chart here, which is shows us a visualization of how the states, like U.S. states, have swung over various presidential elections up to the Obama-Romney area. And we can see that essentially, like we looked at this visualization before. So what you see is we have on the left here democratic states, and then we see, for example, Hawaii is usually very democratic, but in the Kerry-Bush race they only were like 8% more Democratic than Republican, whereas in Obama times they were about 40% more Republican. Of course, him being a Hawaiian is clearly helpful here, and so we can kind of like drop down into the story and explore quite ourselves. So there isn't really like a narrative structure here, right? So what's the genre of the story? What's that?
Annotated chart.
Yes, it's an annotated chart, right? It doesn't use any like thing temporal. We simply can like look at the chart and then interact with it. Is it author or reader driven?
Reader driven. This
is very reader driven, yeah. So nobody is imposing a structure on us other than you tend to start to read on the top. Is the story opinionated or neutral?
Neutral.
Yeah, it's completely neutral. There is no biases in there at all. What do you think about the interactivity? Did it use as well? Yeah, so this is a great example for a story where we have like essentially, we simply can explore a data set ourselves. It is rich, it is annotated, some important highlights are described, but it's this very open and not very author-driven story. Okay, so that concludes the storytelling, and now let's talk a little bit about visualization design and evaluation. And so for that, I like to distinguish between two types of visualization design. There's the problem-driven approach and the technique-driven approach. The problem-driven approach is kind of like this top-down approach, where you identify a problem encountered by some real users, like some real problem in the wild, and then you design a solution to help users work more effectively. This is in the visualization literature, we sometimes call this a design study. And this is really the key point here, is that we're trying to solve a real problem, be it of a scientist or like a general audience, it doesn't matter, but it's the goal is to solve an analysis problem. It's not to develop a new visualization technique. In contrast to that, we have technique-driven approaches where we have a bottom-up approach. And so here is things like invent new visualization techniques or algorithms. So for example, I define some kind of objective criteria, what is a good graph layout, I want to minimize edge crossings and so on, and then I come up with a new graph layout algorithm. That would be a technique-driven approach. So here you can then classify or compare against other visualization techniques or algorithms. So this is like, here is like this very technical approach. We want to improve something or we want to invent something without necessarily having a specific data set in mind, whereas is the problem-driven approach, we try to solve somebody's real problem. And so, who wants to give a quick summary of this paper? Any brave souls? Yeah.
So they kind of present this abstract model of a visualization design and kind of different concepts that you have to cover in different threats at each different level.
And what's the point of this model?
The point is that you can, I guess, kind of like cover all your bases. That like you're designing in a way that makes sense for the problem, and then after that you're doing it in a way that's useful for the users.
Yeah. Okay. So we have two stages, right? We have the design stage and the evaluation stage in this model, right? And they're always at these multiple nested levels. Did you like find any did you find this familiar from your projects? Did anybody find any stages? Like what kind of stages did you like? Let's just put on the stages here. So we have the domain problem characterization, the data operation abstraction design, the encoding interaction technique design, and the algorithm design. What are the stages that you guys probably went through in your class projects? So did anybody do their class project based on somebody's real scientific analysis needs? Like raise your hands if you did that. Yeah, so there's a couple of people that actually collaborated with end users to understand what was going on. Who of you just found an interesting data set and then built a visualization technique around it? Majority. So where did you guys start? Did you think about what are the tasks that you want to do with this? So I see a couple of heads shaking, I have a couple of heads nodding. So there's like data operation abstraction design. If you thought about like who could, like you probably came up with something like a persona of who could your user be, right? What are the kinds of questions that they want to ask? And that is kind of like this data operation abstraction design step. And after that, maybe some of you started at this encoding interaction technique design step. And that's also mainly what we've been talking about in this class, right? What are our choices for these encodings or for these interactions? And then at the lowest level here, we have the algorithm design step. And so we didn't talk too much about this. This is things like, how does the force-directed layout actually work, right? How do we implement this? What is the performance of a force-directed layout? These kinds of things, or the tree map layout algorithm, and so on. So our focus in this class was mainly on this encoding interaction technique design focus. And there's other classes that I'll hint at that will talk more about this domain problem characterization and data operation abstraction design steps. So, what is the purpose of this nested model? Just to recap what you said nicely, the idea is to capture design decisions, and also to be able to justify what is going on in our design, and then analyze the aspect of the design process. And we break this up into these 4 different concerns so that we can essentially be very explicit about in which phase of this design we are, and kind of like not get ahead of ourselves. So this also helps us avoid things like, oh, I have developed this great heat map, and now I'm going out and search somebody who needs a heat map, right? We go out to find people with real data analysis problems, and then try to find what is the suitable tool, instead of just like using our hammer that we have in our toolbox. And then this model is also very suitable because we can validate as often, as early as possible and as often as necessary, so to avoid making ineffective solutions. And so here is this like more detailed version of this figure and the various threats and the evaluation approaches at these stages. So we have at the domain problem stages, we have the problem that the threat that we pick a wrong problem that is not actually what our domain collaborators have. And we can validate by, instead of just talking to them, we can, for example, or instead of making any conclusions on ourselves, we can interview them in detail. We can observe what they're actually doing to understand what is the actual domain problem. And then at the data operation abstraction design problem, the threat is of course that this doesn't work quite so well. However, we don't really have a good way of validating before we go down into the model. So then on the encoding interaction technique design level, we have the threat of using an ineffective encoding or an ineffective interaction technique. And so we kind of can tackle that by being very rational about our choices for encodings. Like we've learned a lot about the hierarchy of visual channels, so we should always be able to justify our choices. That's like one way of validating early here. And then finally we have the threat of a slow algorithm. We can analyze computational complexity before we implement it as a validation approach, or we can measure after we have implemented. And then for encoding we can validate with qualitative or quantitative studies. We can run lab studies, we can measure human time, errors for operation. So this is like the broad area of user studies, where we like test people, where we do things like mechanical Turk, or where we do laboratory studies. And on the data operation abstraction design level, we test on our target users. Like in the green area in the encoding design, we can test on arbitrary people. So this is when we do a user study with 15 CS students who are your lab mates essentially. Here is where we have to actually go back and talk to the real users and see how the real users are using it. And so here we collect anecdotal evidence of utility and we document human usage of the deployed system. And then to validate that we actually did something that was useful, we observe adoption rates. And that's kind of like the model of how we can design and evaluate visualization techniques. So in the domain characterization stage, it's really about finding out the details of an application domain. Like who are the users, what is the target domains, what are their questions, what is their data. And this is something that is like very different by domain. But it must also be specific enough to continue to the later stages. Like I've had a lot of projects where we kind of met with potential collaborators and they had like some kind of data somewhere in the future, but weren't quite sure what it's going to be. So this was clearly not a situation where we were able to do a proper domain characterization. And then the other thing is we cannot just ask people what they want. Like Henry Ford is always like quoted for this like if I just asked people what they wanted, they would have said faster horses, right? Like you might hear, I just want to have an interactive bar chart, but maybe that's not the solution that they need. Maybe they need something completely different. So people don't know exactly what they want. This introspection of telling people what they actually need is hard, and so you have to kind of like engage with them. And I'll be talking about a couple of methods on how to do this later. We also have like an infinite number of domain tasks. So like there's hundreds of different domain tasks for every single data analysis problem that you can have. But the thing is, we can break them down into simpler and more abstract tasks that we know how to tackle in visualization. And the main thing about the main problem characterization is to make this step from what is the abstract domain tasks, like I want to compare gene expression between those, or I want to see how those gene expression values relate to each other, to a specific abstract visualization task, like compare two tabular matrices. And if we have actually identified the task and data combination, there are solutions out there, and we've talked a lot about a lot of those solutions here. On the data and abstraction level, this is really the what and why, where we try to map what we've done in this abstract space, in this like domain-specific space, into this abstract space. We identify the task that the user wishes to perform, or they already do. Define the data types and a good model for the data, and we must also sometimes transform the data for a better solution. Like this is something that you probably also have experienced in your final projects, that the raw data isn't always what you need eventually, but you have to do some kind of data transformation, some kind of cleanup, aggregation, and so on. Under encoding and interaction, this is really where like all of the things that we talked about in this lecture comes in, where you essentially pick design idioms or visualization technique for your problem, for these tasks. We have then different ways to create and manipulate the visual representation of the data, and the decisions on which of these visualization techniques, they may be separate, but they may be dependent on each other. Like if we have multiple data sets, multiple tasks, we have to design them together. And the visualization design principles that we mentioned, like the expressiveness principle and others, they drive these decisions. And so this is like a simplified map of this process. We start out with understanding the domain problem, we map it to abstract tasks, then we understand the data type and other factors that play a role here, and then we can identify a suitable technique. That's kind of the key here. And so here is an example. This is from a paper that I wrote, and like in our community it's quite common to actually explicitly state these things. Like in here we classified domain goals. This was the domain goal here was to control the data quality in alternative splicing data sets, because this is like a noisy data analysis, a data collection process, and it's also a noisy algorithm that produces some heuristic results which we're not completely sure about. So controlling the data quality was kind of like the domain goal. And that we can break it down to a couple of more specific tasks. Things like judge the magnitude of samples, to compare samples, to compare groups of samples. Are there any massive outliers? Is there anything consistently wrong? And so we actually reported, as you can see here on the right, on these domain goals in detail. Say that like control data quality is one of those goals. And then down here in these like more specific analysis tasks, we refer back to what are the domain goals that those actually address. And so now, we implicitly talked a lot about those tasks, but now I want to talk explicitly about these various analysis tasks that we have in visualization. And so we kind of have three levels here. Like first, the high-level analyze level, where it's about do we actually just want to consume a visualization, or do we actually want to produce something, or is it exploratory, or is it just, do we just want to essentially be informed? Is it consumption? On the middle level is searching, finding a known and unknown item. On the lowest level is querying, finding out about characteristics of an item by itself or relative to others. This might sound a little abstract, but I'm trying to make this a little bit more concrete now. So what do I mean by consume? We have these two major aspects of visualization that we have here, like discovering something new, like without knowing something prior about a data set, I go in and find something new. It's like exploratory data analysis versus presenting something that I already know to somebody else. And then on the same high level, we also have produce. So we can do things like annotate a data set that we find, we can record an analysis session, or we can derive a data set. For example, we can derive a network structure from a table data set. And deriving here is very often a crucial design choice. These mid-level actions, such as search and query, are probably what you more commonly think about tasks. Like for searching, we have to distinguish between whether we know what we're looking for or not, and whether we know where to look or not. And so if the target is known, but the location is known, we simply look it up. If the target is unknown, but the location is known, we browse around the location and then we'll find the target. If the target is known, but the location is unknown, we have to locate it. And if neither target or location is known, then we explore. And then we kind of like try to find patterns in the first place. And then for the query step, we ask things like we need to identify points, or we need to compare two data sets, or we want to see a summary. And this is like this, how much of the data matters? Do I only care about one point? Do I care about some points, or do I care about all of the data? And so here's a good example for comparing and also for deriving. This is a visualization of a couple of different recessions in Britain in 2008, in the euro area in 2008, in Greece in 2008 and the Great Depression in 1929 in the United States. And this shows us the change in GDP, I think. And so we see that the Greek economy from 2008 and 14 resembled a lot the Great Depression in the United States. And so this is like a comparison task, right? Here we have aligned by the start of the recession, not by the year that they happened. And so we can easily compare between what is going on in Greece and in the United States. And we can see that there's also, by comparing, we can see that there's also quite a difference in how the impact of the recession in 2008 hit Greece compared to Britain and other Euro countries. And then they also did, the authors here also did derive the data set. This shows us, and this is something that I emphasized also when we talked about tabular data visualization, very often it's better to visualize change than to visualize raw data, right? This kind of like allows us to show axes on a better scale. So here we essentially see that in Greece the change was consistently, like it was getting worse and worse and worse, and then they still lost economic power, but then finally around year 14 there was a little bit of growth again. So this is an example of where we can, where we have a comparison task and where we have a derivation task built in. On the lowest level we have various targets. So we can try to identify trends, outliers, or specific features. And then we can look at attributes where we care either about a distribution of a single attribute or the extremes of a single, the extremes of an attribute, or we can look at dependencies, correlations, and similarities. And then there's specialized tasks for network data where we want to explore topology. We talked about this when we talked about graph visualization, and to see shapes. We talked about this, we didn't talk much about this. We talked a little bit about it when we talked about geographical data, but this is what you will talk about if you attend the scientific visualization class next semester. So here is an example also from the New York Times, the housing bust. We can look, this is also a nice storytelling example, but here in this case I really want to look at like the tasks. So we see, for example, here we can, we have what the impact of the housing bubble or the housing bust was on various jobs. We have things like home healthcare services here, outpatient care, office of physicians, and then above the axis here we have that the number of jobs are increased, and then here on the x-axis we have the jobs classified by higher wages or lower wages. So here we have low wages with residential disabilities, and then physicians here on the right side. And so we can then go on and spot outliers. Like here, for example, spotting outliers is the tasks that we want to do, and we can see that all of these outliers, or like this outlier here, for example, land subdivision, home builders, architectural services, they're all related to the housing bubble. So things that directly relate to housing were worst affected by the housing crisis. So now I want to do an exercise for task abstraction. I'll give you a handout soon, but the idea is that you guys, like I'm trying to simulate you being actually approached by the main scientist to help with the visualization problem, in this case a geneticist. She has gene expression data, that's data that measures the activity of the genes for 30 cancer tissue samples. She's applying an experimental drug on these tissues to see whether the cancer tissue dies as she hopes, but she finds that only some samples show the desired effect. She believes that the difference between the samples is caused by differential expressions, so different activities in these genes, in one particular pathway. So that means a network of genes that has a special function. And she would like to understand which genes are likely to cause the difference and what role they play. And so what I want you to do is to do a task abstraction and then encoding design. And I'll give you about 15 minutes. I have the handout here. And in the task abstraction, like you should kind of take these domain-specific goals of understanding what are the genes that affect whether this drug works or not to visualization tasks. And then in the encoding step, you should actually come up with a plan for which visualization techniques to actually work for this particular problem based on the data that you have and based on the tasks that you identified. You mind helping me? Need more?
Yeah, that's it, no thanks.
So you're welcome to do this in groups. And I'll give you about 10 minutes. Okay, you should start thinking about your visualization techniques that you would use. We'll discuss it in a couple of minutes. Okay, so does anybody want to talk about what tasks you've identified, which abstract visualization tasks, and what domain problem match to?
How the genes are interacting in different samples and which are the genes that are causing the difference in each sample?
Yeah, so that's the domain problem, and how do you map that to the abstract visualization tasks?
I'm not sure if I'm correct, but basically how the gene is interacting with another gene.
That's one part of it, so that would be like the topology task, right, for a network. Anybody else come up with another task? Like, how do we identify which of the genes are actually like relevant for this question? Why does this medication work in some samples and not in others? Like we know that in one of the 30 genes, we have some samples that react to the drug, the other samples that don't. How do we identify which of those? Like, what is the responsible gene?
Q-like probability is like the number of times it occurred in a successful patient over the number of times it occurred overall.
well, computing is one approach, but if you do it with visualization, but you
Well,
said
that's the first step.
you said one important part here. You said compare, and so essentially what we do is we need to compare between them. So let's take a look at this. The task abstraction. So we say only some samples show the desired effect. So we have we can now kind of like from this we can conclude we can derive this like a new data type which is has or has not, right? So it's we can split it up into two groups. So this would be the derived task, our very first task, and then we have the difference between samples is caused by differential expression of genes in a particular pathway. She would like to understand which genes are likely to cause the effects, to cause the difference. So this is a couple of tasks that we have to do here. We first have to identify which of the genes this are. Like in our gene expression data set, we usually have many more genes. So first we identify the 30 genes that are in this pathway. Then we compare the gene expression of those genes between the two groups. So we run the comparison task, and then we identify the outliers, like which genes are different between those two groups. And so these would be kind of our abstract tasks. Okay, and so what visualization techniques could you use to address this problem? So what's the data first? We have a table and a graph, right? What visualization technique could you use for the tabular data?
You can try clustering samples, do some multidimensional scaling, cluster samples based on gene expression.
So do you think that multidimensional scaling would be a good fit if I want to identify specific genes? Like what would you plot? Would you plot the genes as the projections or the samples as the projections?
I was thinking the samples, you have to compare it with some other view that was linked to it, so you could select a group and show, okay, what's the gene profile of this particular sample.
Yeah, so I actually thought about MDS too. The problem with MDS is that we want to see the correlation, what separates those two, what separates these two groups of samples, and what's the cause behind that. And MDS kind of only gives us an overall similarity of samples per genes, right? We can see there might be like a cluster of genes. We could probably identify the genes that cause this difference with MDS, but we wouldn't be able to really be sure, like is it low or high that causes this and so on. So there's a little bit of a problem with MDS. What are other tabular visualization techniques? So dimensionality reduction is one option. Scatterplot matrices. Would scatterplot matrices work here? We have about 30 dimensions. That's a little much for scatterplot matrices, right? So dimensionality reduction doesn't show us raw data, and it's not great to compare groups. The scatterplot matrices, we have about 30 dimensions, which is a bit of a problem for scalability. Parallel coordinates.
Yeah, you could for comparison.
Yeah, you could. It's a little much for 30 dimensions, but it's going to work on a big screen. So it's not completely unfeasible. You would have to use some color coding for comparison. Heat maps and bar charts could be like a viable option, right? So in the heat map, we have a very clear spatial separation of the groups. We see the patterns based on the colors. And for bar charts, they probably work even better because 30 by 30 bars is absolutely feasible on a typical screen. And we have the encoding advantage that we can see bars better than not. And so this is a task that I actually encountered in one of my research projects. And this is our solution that we had for this. We came up with a bar chart to show this gene expression. And here at the very top, this is like whether this drug or whether this cell lines react to the drug or not. The high values here show that they react to the drug. The low values show that they don't react to the drug. So heat maps would have been a viable solution if I had more data, if I had 100 or 200 samples, but if I have only 30, then bar charts seem to be also a good approach. And then for the task abstraction, the second question is, what role the genes that are affected play in a pathway? And so to do that, we would have to locate the outlier in the network and then explore the topology. So first we have to find the gene that has this pattern, and then we have to see where is it. in this larger network, right? And this is this topology exploration tasks. And so what visualization techniques would be suitable for that? What other graph visualization techniques, the big classes? What was it? Network, yes, but node link diagrams is the one, yes. And the other one? Matrices. Matrices, tree maps, and node link diagram. Is a matrix a good choice here? No, because we want to explore the topology, right? And we know that matrices are only good for neighborhood-related tasks, so they're clearly not a good choice. Is the tree map a good choice here? So no, the tree map actually doesn't work at all for this data type, right? It only works for trees. It doesn't work for general networks. So we can't really consider a tree map. And so a node link diagram here works well. And then we would do like a multiple coordinated view system where we combine the network with the table, and then we can hover over the genes that are outliers in our comparison, and then we can essentially address this whole visualization task. Okay. So this is what like a node link diagram of a pathway usually looks like. Great, so now I want to take a bit of a step back and talk more generally about design. The question is like, what is design? Like many of you probably think of design as graphic design, like anything that you would do with Photoshop or Illustrator. But what we're talking about when we talk about design is that we want to create something new to solve a problem. Design more generally can be used to do things as diverse as make buildings, make chairs, create user interfaces, and so on. And it's broadly used in many fields, and we have many possible users and many possible tasks. This is a YouTube video. I'm not going to play it, but I'm going to post the slides later. You should look at it. This guy spends 25 minutes explaining the design of a soda can. And it's very interesting, like not the graphic design, it's like why does a soda can look the way it does? And there's a lot of thought that went into a soda can, essentially to optimize how little material you need to use so that it still has is stable enough to be transported easily, it's easily opened, it doesn't produce unnecessary trash, and so on. What is design not? It's not about making things pretty. It's not about art, it's not about appreciation of beauty or emotions invoked. So design essentially comes from the user and influences the product, versus art is something that is supposed to influence people. It's not something without a clear purpose, and it's not about building something without justification or evidence. Form follows function is like a well-known proverb. Functions can constrain possible form. Like the forms depend on the task that we must achieve. A table like this, it serves in like placing things, but it doesn't serve the function of having like a social interaction around a dinner table, for example. And Alberto Cairo, who is like a graphic journalist, likes to say, the better define the goals of an artifact, the narrower the variety of forms it can adopt. So the more precisely we specify what a visualization needs to do, the less choices we actually have. And so by essentially coming up with these very specific tasks and goals, we kind of can drastically reduce our options, because otherwise we would have a massive amount of potential options if we weren't able to reduce them in any way. And why does design matter for this? Because there's simply a lot of ineffective combinations of visualizations. We have a lot of users with unique problems in data. We have a lot of variation of tasks. We have this really large design space. As you remember, we have like in our textbook, we saw it as like what, why, and how, and these are all the different options that we have to consider when we design a visualization technique. Who's heard of wicked problems? So there's a concept in design that's called a wicked problem. These are problems that don't have a clear solution, where we essentially can find solutions that satisfies it, where we can kind of like, yes, that works, but we cannot say this is the best possible solution. There is no clear best possible solution. There's no clear end goal. There are multiple solutions. None of them is absolutely correct. And there's also no clear point to stop with the solution. So essentially, things that we can, like a wicked problem, is very common in design. We have to find something that works, but it's unlikely that we will find one thing that is always perfectly correct. Examples for non-wicked problems are things like puzzles, or some kind of like proof in mathematics, or chess. These are like tame problems where there's clearly like a winner, a true or false, which is not the case in many design problems. Like I can like route a highway in many different ways. Most of them are going to work, some of them are going to work better, some of them are going to work less. I can design less well. I can design an intersection so that it's optimized for both bicyclists and drivers, but is one intersection design better than the other? It's not quite clear. The same is true for visualization. And that kind of makes it hard for, if you develop visualizations, to claim that your new visualization is actually better than anything that is out there. And we'll talk about how we can evaluate what is good or not, either today or I'll briefly talk about it on Tuesday if we have the time. So there are methods to design. Like most of this class is about essentially giving you the background knowledge to make these informed design choices. But there's a couple of other things that you can do to arrive at a design as good as possible. So one thing is parallel prototyping. Like what we've done in all of our exercises when we did redesigning class, I always asked you to do multiple designs of the same thing. And that's because if we just do one design, we very quickly get like locked in mentally into one particular path. So this is like from a paper where they asked a group of people to do some graphic design for a magazine, and in one case they asked them to do a couple of iterations, and you can see that from the first to the last one there's very little variation here. And in another group they asked to do like parallel designs and then still iterate on them. And you can see that the parallel designs came up with something completely different initially, and then they refined them and came up with a solution that incorporated elements from multiple of these initial designs. So parallel prototyping is a very important approach. There's a couple of specific approaches in visualization. I'm not going to go into too much detail, but this is so that you have references if you want to look at this in more closely. There's the 5 design sheet methodology, which is tailored for visualization design and is actually used in classroom and in industry. And it uses a lot of sketching, and it essentially has 3 phases with 5 sheets. There's the one brainstorming sheet. Then we have different principal designs in sheets 2 to 4, and then 5 is this convergence sheet where we kind of take ideas from the sheets 2 to 4 in detail. And there is like this website, fds.design, that describes this methodology in detail. Then there is visit cards that essentially assists novice visualization designers with understanding the space. So there's cards for the things that we just talked about, like the tasks that are possible, and then for the different visualization techniques that are available and so on. And so this is like a physical reference for all the things that you potentially can do based on these cards, and this is at visitcards.org. And then something that you might have heard if you took an HCI class is paper prototyping. Like sketching is the first step, right? But once you have arrived at like one design that you like, you shouldn't immediately go into D3 and hack, but you should rather come up with a little bit more sophisticated sketches where you even like simulate some interaction. So here you can see that this is not like one sheet, but they actually sit down in front of a user and show them this is the initial screen, and now you can click here, and then once you click here you give them like a new sheet, and so on. And so you play essentially like a game of like the user interacts and then you simulate it by placing paper around. And that is like, there's a lot of studies that show that people, like especially your end users, are much more open to give you suggestions of what works and what doesn't, compared to when you show them functional prototypes. because people have feel like, oh no, you've so invested so much time, and now if I think this would work better, otherwise I'm kind of placing a burden on you. That kind of inhibition doesn't exist when you use paper prototypes. So users request more features to add and more changes, and paper prototypes support creativity and interaction. And then one thing, especially for this domain characterization step, that I find very helpful, because this is a really hard process of getting to know what people actually want from you, are these creativity workshops. This is the research area of one of our PhD students in the lab, Ethan Kertzner, and he has developed a method where he brings a group of experts into a room and runs these creativity workshops that contain brainstorming, but also some things like wishful thinking and then constraint removal. Because very often experts, they think, well, it would be nice to do this, but we can't because B. And then you say, what if B didn't exist? What could you do then? How could you approach this then? And there's a couple of other things like analogical reasoning, storyboarding, and so on. And I've personally run a couple of those, and it turns out that essentially you can get to understand your user needs in a day what would sometimes take you months otherwise. So this is a very effective way of understanding the needs of users. There's some other methods, like interviews are kind of the standard methods of trying to understand people, and observations like embedding yourself in the lab and observing the actual work process of your collaborators, qualitative analysis, coming up with personas is a well-known software design method, like who are my stakeholders, there's the manager who has only 15 seconds to look at my interface, there's the administrator who prepares that for the manager, and then you come up with these different personas. Something visualization specific is data sketches. These are different from paper sketches. These are where you actually draw with data. So that can be as simple as drawing faithfully in Illustrator on real scales, or even doing some rapid prototyping using coding. So these are all other methods for doing design. And now I have about 8 minutes left to talk about evaluation. So I'm not going to go into details. There's a lot of other courses that teach evaluation methods, but I'm just going to give you a bit of an overview of what is the role of evaluation and validation. The underlying goal is we want to avoid ineffective solutions, but especially as academics, we want also to be able to justify our solutions. Why is something that we did better than something else? And I like to think of two dimensions that play a role here. Especially for visualization. Is this something perceptual, something that I can reliably test with a broad population, or is it an intricate system that has many things where I interact, where I have to import data, where I have multiple views, where I simply cannot isolate one thing very clearly. So for example, a perception question would be, is size a better visual channel than angle? We can easily design an experiment to answer that question. We can do this in a lab study. We can deploy it on Amazon Mechanical Turk, and we will find an answer to that. But is my pathway visualization system any good? Is not as easy to answer, right? We have a much more fuzzy definition here. And then there's this other dimension, unique versus comparison. This also applies mainly to systems. Can I easily compare my visualization to others? Am I the fifth system, am I the fifth graph visualization or graph layout algorithm? I can easily make comparisons. Or did I create something that is unique of a kind, where there isn't anything comparable? And that kind of influences your choices for your evaluation techniques a lot. And then, parallel to this, these are evaluation and validation considerations, but sometimes you also want to just understand whether the usability of the system that you created is good, or whether there are any problems. And I'll talk a bit about methods specifically for usability testing. So I want to show you a simple example for a perception comparison experiment. This is I think I showed this in the perception lecture, but this is 3 different visualization techniques to show highlighting in a simple web browser. And so we have 3 conditions. It's static, it's very easy to control. So we can do a controlled laboratory experiment. We can measure things like performance, how quickly did people identify all of the targets, did they actually identify all of the targets correctly, and so on. And we can create hypotheses and then validate this hypothesis by measuring things like average search time and average misestimation. And so it turns out that in this case, like, our hypotheses were true, and in this case we were even able to do eye tracking on top of this. So we can see that there's different ways of how people interact with those systems. But again, this works only for this very, very narrowly controlled setup. In contrast to that, this is a project that our TA Carolina is working on right now. This is a system for visualizing large genealogies and clinical data to identify environmental and genetic causes of suicide. We're looking at really big genealogical graphs with hundreds of disease codes in addition, and genetic data and so on. There is no other system like it. It's not a visualization technique. The best comparison is a system like this that shows us the same data set here, and it's barely readable. So we have a problem here. We can't say our system is better than this because that's obvious anyways, right? How can we say our system is still a good system? Well, one approach of doing this is to run a case study. So here in case studies, you demonstrate the usefulness for your domain scientists. You go in and give them the systems and let them use it independently if you're watching them over their shoulder, and then see whether they can find things that they couldn't before. See whether it's actually useful in their context, and then report on these cases of where they found novel insights. There's lots of other Visma evaluation methods out there. There's of course the controlled experiment, which can be either laboratory-based or crowdsourced. We can do interviews and questionnaires. These are very often combined, so you first run a controlled experiment, then run an interview. You can do field observation or lab observation. Field observations have high ecological validity. We talked about this concept when we talked about crowdsourcing. And lab observations have a little less, but still these are kind of methods where you need to have real prototype or real software out there, and then you can do things like record people using it. You can do video and audio analysis, and then you code, you come up with a coding scheme, and you classify user behavior or what people said or the gestures that they did and so on. You can instrument your system to allow log analysis. You can measure performance if that is possible. You can do things like heuristic evaluation in cases where you have something like a recognized usability metric. You can do usability testing, for example, thinking aloud tests. The thinking aloud tests are a form of usability testing where you ask people to use your system and simply think out loud of what they're doing. Oh, now I don't know what is going on here. I'm going to go to this menu and see whether I find this option, and so on. And by using that and transcribing that, you can spot usability problems. This is not a method that is suitable for evaluating your system. It's a method that is made for the designer to spot problems with the system. A very interesting method is the Wizards of Oz method. Here, essentially, you fake everything. There's nothing that is really implemented. You tell people just interact in some way, and then a human gives the response. It's a good example that I saw once is a charting by example study that some people did. The question was, how can we let people draw, sketch a visualization technique, and then let the system choose the visualization technique? And so what they did, the users sketched on a computer screen, and then they saw an operator saw, okay, they were trying to sketch a line chart, and then showed them, did you want to sketch a line chart? And so they could kind of evaluate how people try to sketch these techniques and how they react to the results without actually having to implement it. Then you can do eye tracking or expert-based evaluations or insight-based evaluations and case studies. I mentioned case studies. Just to conclude with, I want to talk a little bit about insight-based evaluation because that's kind of a method that is kind of accepted in visualization or of comparisons. And the idea behind insight-based evaluation is that you capture like what did people actually learn in some kind of like middle ground way. Not this like, oh, I found an outlier, and not this like, oh, this gene causes cancer, but in these like, oh, there is a correlation between that, and this is interesting. And so there's a way of codifying those insights, and then you evaluate two systems and compare how many insights did they enable per minute, and things like that. And that's how you can make an argument of why one system is better than the other. So I'll stop here, and good luck with the rest of your project, and then I'll see you on Tuesday for the best project presentations, and then on Thursday for the exam.